So let's talk about law of cosines. But first, before we talk about law of cosines, I want to introduce the idea, and we'll dig a little more into this as we talk about the unit circle, but introduce the idea of talking about triangles instead as coordinate points. You'll probably hated coordinate geometry when you did it in high school. Everyone does for some reason. I loved it personally. I do geometry in my professional mathematics. But here we want to talk about triangles instead as a coordinate point that forms a triangle. So if I take my coordinate grid that's supposed to be straight lines, but I can't draw, and I draw a point, which is x, y, this forms a triangle. I can draw a line from the origin up to the point, and then back down to the x-axis, and I form a triangle. And so instead of talking about trig functions in terms of sides and just sides, we can talk about trig functions in terms of coordinate geometry, which becomes really useful, especially when you apply this stuff to, say, physics or anything like that. So the length of this base is x, right? Because I have to go over x and then up y. And then this right here is y. Then we can find the other side just by using the Pythagorean theorem. I have x squared plus y squared equals, I'm going to call this r squared. So r equals the square root of x squared plus y squared. You might remember from algebra that if I take a square root, I should have a plus and minus here. Why do I not include the plus and minus? Distance can't be negative, so there's no point in including a minus if my distance can't be negative to begin with. So I can talk about my triangle formed here in terms of coordinate points. I can then discuss all of my trig functions as such. So for instance, I remember sine of theta, if this is my angle theta here, what's markers? It probably does. Actually, I took a shower this morning, so it probably does. So sine theta, we remember, is opposite over hypotenuse. Here my opposite side is y, and my hypotenuse is r. Or writing out what that hypotenuse actually is, that's the square root of x squared plus y squared. Cosine, similarly, we said was adjacent over hypotenuse, which here is going to be x over r, or similarly x over x squared plus y squared. And then tangent, very simply, is opposite over adjacent, which here is y over x. So I think I've mentioned in class at some point talking about trig functions in terms like this. And that's where this comes from. Thinking about trig functions instead of being just sides, but instead represented by coordinate geometry. It becomes very useful when we talk about points. The reason I introduce this is because it's really useful to prove a special identity of trigonometry using these representations. One thing I want to look at is if I take sine of theta, which I'm just going to say is y over r. If I square both sides, and when we square sine theta, we put the square after the sine, which just means I apply sine and then I apply sine again. If I square both sides, then I very clearly get y squared over r squared. And if I do the same thing with cosine squared theta, that's going to be x squared over r squared. All right. And then what happens if I add them together? Sine squared theta plus cosine squared theta. Sine squared theta is y squared over r squared. Cosine squared theta is x squared over r squared. Those have a common denominator, so I can just put them over the same denominator. X squared plus y squared over r squared. Well, what is r squared? r squared, I just square this side, would be x squared plus y squared. So I plug that in right here. I get x squared plus y squared over x squared plus y squared, which is 1. So all of that algebra is to show a very useful result that will become handy, is that sine of any angle squared plus cosine squared of any angle is always equal to 1. This is the exact same thing as the Pythagorean identity, but written in trig functions. A squared plus b squared equals c squared. This works out just like this when it comes to trig. Cool. So that's just a quick little, more or less, proof of that fact, which is useful for what we want to do next. Are there any questions about this? You don't have to memorize all the steps of the proof. The only thing that's really important is this part right here. I more or less just introduced the x and y thing so that you had some basis for this proof. We'll revisit this when we do the unit circle. So we'll actually really dig into that then. Any questions about any of this? I'm going to erase the right side of the board here. I'm now going to use this fact to help me derive what we will call the law of cosines. So I'm going to take a triangle, and just like we did with law of sines, I'm going to notate it so that an angle across from it is the lowercase of that letter, just because it is useful. This one was C, capital C, this is capital B. I'm now going to think about this circle in terms of the coordinates of these points. The way I'm going to do that is I'm going to set it so that this angle A is at the origin of our coordinate plane. So that point is 0, 0, and then this does follow along. So A, that angle A, which we write as angle A, I wrote my angle a little weird, but it's supposed to look like an angle, not less than A. I'll just write out the word angle, how about that? Angle A is at the coordinate point 0, 0. Right, the origin is the point 0, 0, recalling from algebra. Angle B then, its x-coordinate is C, because this distance is C here. And then it's at y equals 0, it's on the x-axis. Then how do I find angle C? What is its position? Well, I have to use a little bit of trig here. I can call this vertical piece y, and this horizontal component of it x. So I get this little triangle inscribed here. This is x, y, and angle A, and this is B. Y, I want to relate this angle with y and the hypotenuse. Opposite over hypotenuse is sine. So I have sine of A equals y over B, or y equals B sine A. And then x is going to be cosine, because it's adjacent with hypotenuse. So cosine of A equals x over B, or x equals B cosine of A. So my x amount is B cosine A. I go over that much, just forming this little right triangle. My y amount then is B sine A. So the coordinate point for C is x is b cosine of a, and then the y value is b sine of a. Right? This kind of makes sense. Y corresponded, oh, I erased it. We said that y, or sine was corresponding to y. Sine of theta equals y over r, and cosine of theta corresponded to x. And so it makes sense that my x value is cosine, my y value is sine. Makes sense here in this construction. All right. So now I have these coordinate points. Say I'm trying to figure out a here, I can use the distance formula. This might seem a little counterintuitive, and all of this really just is for the proof, so you don't have to 100% memorize all these steps. It's just kind of proving where this, or deriving this law of cosines. So I have the difference between these 2 points. Remember that the distance between 2 points, I'll call them, I'll just say this. The square root of the difference of their x values squared plus the difference of the y values squared. Right? That's just rewriting the Pythagorean theorem fancy. And so if I take the square on both sides, it's x1 minus x2 squared plus y1 minus y2 squared. Cool. So the distance between this point and this point is a, right? It's separated by that side length a. So I can rewrite this distance formula in terms of our triangle over here. I have that a squared equals the difference in x coordinates. So I subtract my x coordinates. So that's going to be b cosine of a minus c. B cosine a minus c, that's the difference in x values. I square that, and then plus the difference in y values. It's going to be b sine a minus 0. And then I'll square that. So again, all I'm doing is I'm figuring out a by using the distance formula. Talking more in coordinate geometry right now, so that's where that's going to do. All right. I can then factor this out, or distribute, I guess. So it's going to be b squared cosine squared of a, and then minus 2bc cosine of a plus c squared. So that's if I factor out this first one. I'm not going to walk through most of the algebraic steps because we should be mostly familiar with these, or at least decently comfortable. So whenever I do an algebra step like this, I'm not going to walk through it. But if you want to walk through it on your own time, you're more than welcome to. And then over here, just squaring this minus 0 is the same thing as just this. So I don't even need to worry about this minus 0. And I just get b squared sine squared of a. So I'm going to rewrite this result right here so I have a little bit of room to work with. So I get a squared equals b squared cos squared of a minus 2bc cosine of a plus b squared sine squared of a. I've got this b squared term here and this b squared term here, so I can put them together and factor out the b squared. What I mean there is that's the same thing as b squared times cosine squared of a plus sine squared of a, and then minus this 2bc cosine of a. And now we see the reason for why I proved this earlier. I have a sine squared plus cosine squared in there. So this inside part here is 1. And I'm left with b squared. Oh, and I missed my c squared. I dropped it somehow. There's a plus c squared there. I apologize for that. I just didn't copy it over. B squared plus c squared minus 2bc cosine of a. So this looks like the Pythagorean theorem, but I have this extra thing here. And conveniently enough, if cosine of a, if the angle a is 90 degrees, this is 0, and I get the Pythagorean theorem. So this does turn out the Pythagorean theorem if I have a right triangle. Pretty nifty there. This is true for the other angles as I swap them around. If I just take and put the origin in other points, I could derive these out, but I'll just write them out for you. B squared equals a squared plus c squared minus 2ac cosine of angle B. And then c squared equals a squared plus b squared minus 2ab cosine of angle capital C. And these are true for any triangle that is notated this way. So, a decently long, complicated proof, at least for our standards, but that derives these formulas for us that are really useful. Remember when we were doing law of sines, we had to have a pair of an angle with an opposite side to be able to do law of sines, plus another piece of information. This takes care of cases where I don't have that. If I have two sides in any angle, I can solve the rest of the triangle. So, using law of cosines and law of sines together, I can deduce a lot of information about triangles very quickly. This seems like a bunch of just random nonsense that I've spouted at you for the past 15 or so minutes. So I'm going to see where we actually are going to use this trigonometrically. Again, you don't have to memorize all the steps of this proof. The important thing is that these are our formula that we use. And then this is the triangle that corresponds to such formulas. Just like law of sines corresponds to a triangle like this, but the equations are different. Take, for instance, we want to solve this triangle. I know this angle, which I'm going to say is 82.4 degrees. And I know these sides. This is 212. This is 388. The setup of this problem is I'm standing some distance away from a tunnel. I know I want to try to estimate the length of the tunnel. If I know the angle from where I'm standing to each side of it, and then the length of my distance from there. So I'm trying to estimate this here. And this is where we're going to use law of cosines. Again, remember in law of sines, I had to have a side with an opposite angle to be able to do anything. I don't have any of those pairs here. I'm missing this side, and I'm missing these two angles. So we have to resort to law of cosines instead. I'm trying to figure out this missing side, which I'm going to call x. And the process for solving law of cosines instead of law of sines, which I pick a pair at another point, is I take the opposite side, the one that I'm trying to figure out, and I let it be the left-hand side here. So I get x squared equals, I then have my other two sides, so that's 212 squared plus 388 squared minus 2 times the product of those sides, so I'll write that down in the line below, minus 2 times 212 times 388, and then the cosine of the angle between them, which is 82.4 degrees. Again, it's important that I note that it's degrees here, so when I go to put this in my calculator, I have it in degrees instead of radian, and I get the correct answer. Cool. So all I've done here is I've set up law of cosines, where A is my missing side length, B and C are the side lengths that I'm given, and the angle is the angle between those side lengths. So again, the setup is always put your unknown on the left side. Your other two sides are going to be your sides that you have, and your angle will be the angle between those two sides. Now I can go through and just punch this in my calculator. Doing so, I should get x squared is approximately 173,730. And so taking the square root on both sides, I get x is approximately 417 of whatever unit. Maybe these are feet. I then could solve the rest of the triangle using law of sines if I wanted to, but I'm not too worried about that right now. So this isn't extremely different from the process of solving this with law of sines. I just have to pick different information and plug it into a different equation. Remember in our 5-step process that I talked about, the first thing was take all your known information and what's your unknown information and what's relating them. For law of sines, my known information has to be a opposite pair of an angle with an opposite side and one other piece of information anywhere else on the triangle. Here my information has to be two sides and an angle in between them. And then I can figure out any other information on this. So it depends on what information I'm given for what formula I'm going to use. Any questions about this? Is your calculator in radian or degrees?
It is in degrees.
Did anyone else get this answer? Or did someone get something different?
I got it.
You got that answer?
Okay.
Check your typing it in. There might just be an error in how you typed it in or something. I'm gonna go over here. So that helped us to find a missing side. We can also rewrite the law of cosines to solve for a missing angle, just like we were able to solve law of sines for a missing angle by taking the arc sine on the other side there. So I'm going to use this formula here. A squared equals b squared plus c squared minus 2ab cosine, oh that's 2bc, my bad. 2bc cosine of A, and I want to figure out the angle A. I can subtract these over or add this over. Actually, that's what I'm going to do. I'm going to add this term over to the left side. So you get A squared plus 2bc cosine A equals b squared plus c squared. All I've done is I've added this term over to the other side. And I want to subtract out the a squared over here. The reason I did it in this order is just to avoid some negative signs. So I get 2bc cosine of A equals b squared plus c squared minus a squared. And then I can divide by this 2bc. So you get cosine of A equals b squared plus c squared minus a squared over 2bc. And then lastly, I apply inverse cosine on both sides. So I get that my angle, for any angle in there, if I have the size of the triangle, I can then figure out the angles, which is nice. This is equal to the inverse cosine of b squared plus c squared minus a squared over 2bc. So here's another useful formula similar to these. So I'm going to write those out real quick. A squared equals b squared plus c squared minus 2bc cosine of a. B squared equals a squared plus c squared minus 2ac cosine of b. C squared equals a squared plus b squared minus 2ab cosine of c. And I get 3 more equations here too, now each for all of the angles. So I have a way to get all of the sides. I also have a way to get all of the angles. A is the inverse cosine of b squared plus c squared minus a squared over 2bc. B is the inverse cosine of, I picked the other two, so a squared plus c squared minus b squared over 2ac. And c is equal to the inverse cosine of a squared plus b squared minus c squared over 2ab. So I didn't even have to derive out any of these other formulas. I basically just cycle through my variables and notice the pattern. But now that I have this, if I'm given a triangle with only side lengths, I can derive every angle within the triangle using this. Which wasn't something we were able to do beforehand. We were only able to do it with right triangles, given side lengths. But now we have this. Say, for instance, I have a triangle. We tell you the side lengths are 5, 8, and 12. Obviously, this isn't drawn to scale. I apologize for that. And I ask you to find all of the internal angles. Well, I have a way to do that just by using a rewriting of the law of cosines. I can derive all of my angles just using the side lengths. Cool. I'll let A equal 5, B equal 8, C equal 12. It really doesn't matter. But what does matter is where I put the angles opposite from them. A is 5, so this is capital A. B is 8, so this is capital B. C is 12, so this is capital C. Then my angles are dependent on these. For instance, my angle A is equal to, using my formula for this, I'll write angle, 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 angle. It's the inverse cosine of b squared, 8 squared, plus c squared, which is 12 squared, minus a squared, which is 5 squared, over 2 times b, which is 8, times c, which is 12. Any questions about where I got this information? Okay, I solved for these using these, so I solved for the angle. And that gives me a way to relate the angle to the side lengths. So now I'm just plugging side lengths in here to solve for this angle. All right. This is then equal to the inverse cosine of, that comes out to, do I write it down anywhere? I thought I wrote it down, but I guess I didn't. Oh, it did, right here. This is 183 over 192. So this angle is approximately 18 degrees. I can then do b the same way. B is now equal to the inverse cosine of, all right, well my formula says I take a squared, 5 squared, plus c squared, 12 squared, that looks like 52, minus b squared, which is 8 squared, over 2 times a5 times c12 If I punch this into my calculator, I get that this is the inverse cosine of, so simplified as 7 over 8. I believe, let me double check that. 5 squared plus 12 squared minus 8 squared divided by 120 is 7 over 8. Cool. And then this comes out to approximately 29 degrees. And then same thing for this last angle. C is the inverse cosine of a squared, 5 squared, plus b squared, 8 squared, minus c squared, 12 squared, divided by 2 times a, 5, times 8. That's equal to the inverse cosine of, I believe that's negative 5/8, but I want to check that. So 5 squared plus 8 squared minus 12 squared divided by, that's now 80, so negative 11 over 16. Okay, that makes more sense. And if I take the inverse cosine of that, inverse cosine of negative 11 divided by 16, I get approximately 133 degrees. I want to check that these angles add up to 180. 18 plus 29 plus 133, I get 180. So your answer might be off by a degree or two if you rounded like I did, but I rounded in just the right ways for it to work out there. Cool. So we have a plus b plus c equals 180. We're all good. And we were able to solve the angles of this triangle just using the side lengths. And again, this works for any triangle that you have. Tomorrow, we're going to keep on doing this, but with what we call boundedness, or the directions we steer. So for example, if I say someone is going north at 40 degrees east, and then they go north at 50 degrees west, what's their distance from their original position if they traveled so many distances? We can talk about that, and we'll do an example there, which would be useful. That's all I have for y'all today. If you have any questions, obviously you can email me. I'm on my office hours tomorrow, anything like that. And y'all have a great rest of y'all's day.